Today we journey backward through deep time to an Earth so alien that breathing its air would kill you in moments. This is not science fiction. This is the real story of our planet's most dramatic transformation, when the very essence of life became death, and death became the foundation of all life that would follow. Picture, if you will, a world wrapped in perpetual twilight. The sky above is not the familiar blue we know, but a pale orange haze that filters the sun's rays into something softer, dimmer. The air shimmers with methane and carbon dioxide, thick and heavy, carrying the scent of sulfur and volcanic ash across landscapes that stretch endlessly, without a single blade of grass, without a single tree, without anything we would recognize as life on land. This is Earth, 2.5 billion years ago, a planet where the very air that would one day fill our lungs was not just absent, but unimaginable, where oxygen, that invisible partner in every breath you take, was locked away in water molecules, hidden in rocks, banished from the atmosphere by chemistry that had ruled for over 1 billion years. But something was stirring in the ancient oceans, something small, almost invisible, yet destined to reshape every molecule of air, every drop of water, every grain of soil on this planet. This is the story of how life itself became Earth's greatest catastrophe, how innovation became extinction, and how the rise of oxygen nearly ended all life forever. Let us drift back through those unimaginable spans of time to understand how our world's air became poisonous, and how that poison became the very foundation of everything we know today. In the beginning, there was no breath of life as we understand it. Earth's earliest atmosphere was a mixture alien to anything living today, dominated by gases that would seem foreign to our modern senses. Nitrogen filled much of the sky, just as it does now, but the similarities ended there. Carbon dioxide swirled in concentrations tens, perhaps hundreds of times higher than today's levels, creating a greenhouse effect so powerful it kept the planet warm despite a sun that burned 20% dimmer than it does now. But the true architect of this ancient atmosphere was methane. Vast quantities of this invisible gas filled the air, produced by primitive organisms called methanogens that thrived in the oxygen-free world of early Earth. These tiny life forms, barely visible under the most powerful microscopes, were the planet's first great engineers of atmosphere. They consumed simple organic compounds and exhaled methane as their waste, pumping billions of tons of this potent greenhouse gas into the sky year after year, century after century, for over 1 billion years. This methane-rich atmosphere created a world of perpetual warmth. Even at the poles, temperatures remained mild. Ice was virtually unknown. The powerful greenhouse effect of methane trapped heat so efficiently that Earth remained a warm, humid planet, despite receiving significantly less energy from the young sun. Volcanic gases added their own contributions to this primordial air. Hydrogen sulfide, with its distinctive smell of rotten eggs, drifted on ancient winds. Ammonia, toxic to most life we know today, was a common component of the atmospheric mixture. Most remarkably, this atmosphere contained virtually no free oxygen. What little oxygen existed was immediately consumed by chemical reactions with iron, sulfur, and organic compounds. The concept of an ozone layer was meaningless in this world. Ultraviolet radiation from the sun penetrated deep into the atmosphere, reaching the surface with an intensity that would sterilize any unprotected life in moments. Yet life persisted, hidden beneath the protective waters of the oceans, adapted to a world where oxygen was not just unnecessary, but deadly. The early Earth's surface told a story of perpetual chemical activity. Rivers carried dissolved iron in concentrations that would seem impossible today, staining the water red and orange as they flowed toward ancient seas. The oceans themselves were a chemical soup rich in dissolved metals and minerals that would precipitate instantly in the presence of oxygen. But oxygen was nowhere to be found in these waters, allowing iron and sulfur compounds to remain dissolved, in concentrations thousands of times higher than modern seawater could support. This was a world where chemistry ruled supreme over biology. The processes that shaped the atmosphere and oceans were driven primarily by volcanic activity and the gradual cooling of the planet from its violent birth. Life existed, but it was relegated to the margins, to the deep ocean floors, to hot springs and volcanic vents, wherever chemistry provided the energy and nutrients necessary for the most primitive metabolisms. The organisms that inhabited this ancient world were unlike anything alive today. They were exclusively anaerobic, meaning they not only lived without oxygen, but would die if exposed to it. These archaic life forms had evolved over hundreds of millions of years to thrive in an environment that would be immediately lethal to virtually every organism alive today. They powered their metabolisms with chemical reactions involving sulfur compounds, iron and organic molecules, extracting energy from processes that required no oxygen whatsoever. Among the most successful of these early organisms were the methanogens, single-celled organisms that belonged to a domain of life called archaea. These remarkable microbes could survive in conditions of extreme heat, acidity, and salinity that would destroy most life. They thrived in the sediments of ancient seas, in the hot springs that dotted volcanic landscapes, and in the deep crustal rocks where they consumed hydrogen and carbon dioxide to produce methane as their metabolic waste product. The methanogens were not just surviving in this harsh world, they were actively shaping it. Their collective metabolism pumped enormous quantities of methane into the atmosphere, maintaining the greenhouse effect that kept Earth warm and habitable. And in a very real sense, these tiny organisms were the planet's first climate engineers, unconsciously regulating global temperature through their biological processes. But the methanogens were not alone in this ancient biosphere. Sulfur-reducing bacteria thrived in the oxygen-free waters, using sulfate compounds as electron acceptors in their metabolic processes, and producing hydrogen sulfide as a waste product. Iron-reducing bacteria consumed dissolved iron compounds, helping to maintain the high concentrations of dissolved metals that characterized the early oceans. Purple and green sulfur bacteria used the energy of sunlight to power their metabolisms, but unlike their later descendants, they did not split water molecules in the process. Instead, they used hydrogen sulfide and other reduced compounds as electron donors, producing sulfur rather than oxygen as their waste product. This anaerobic biosphere represented billions of years of evolutionary innovation and adaptation. These organisms had developed sophisticated biochemical pathways that allowed them to extract energy from their environment without ever producing oxygen as a byproduct. They had created a stable, self-regulating ecosystem that had persisted for over 1 billion years, maintaining the chemical balance of atmosphere and oceans through their collective metabolisms. Yet even as this ancient world seemed perfectly balanced and stable, the seeds of its destruction were already being sown. Somewhere in the vast expanse of the early oceans, a new type of organism was evolving, one that would develop a capability so revolutionary, so fundamentally disruptive, that it would transform every aspect of Earth's environment and drive the first great mass extinction in planetary history. The story of this transformation begins not with a single organism, but with the gradual evolution of increasingly sophisticated molecular machinery for capturing and using the energy of sunlight. Early photosynthetic organisms had learned to use solar energy to power their metabolisms, but they relied on readily available electron donors like hydrogen sulfide or organic compounds. These organisms were limited by the availability of their chemical fuel sources, restricting their growth and distribution in the ancient oceans. But around 2.7 billion years ago, a revolutionary innovation emerged in the microscopic world of ancient bacteria. A group of organisms that would later be known as cyanobacteria developed a form of photosynthesis that was fundamentally different from anything that had existed before. Instead of relying on scarce chemical compounds as electron donors, These new organisms learned to use the most abundant substance on Earth's surface: water. The evolutionary breakthrough that cyanobacteria achieved was the development of a molecular complex called photosystem II, a sophisticated piece of biological machinery capable of splitting water molecules using the energy of sunlight. This process, known as oxygenic photosynthesis, allowed cyanobacteria to extract electrons from water molecules, using those electrons to power the production of organic compounds from carbon dioxide. But this revolutionary process came with an inevitable byproduct: oxygen. At first, the oxygen produced by these early cyanobacteria had little impact on the broader environment. The ancient oceans and atmosphere contained vast quantities of reduced compounds, iron, sulfur, and organic molecules that immediately consumed any oxygen that was produced. The dissolved iron in the oceans was particularly effective at removing oxygen from the water, oxidizing from its reduced ferrous form to its oxidized ferric form and precipitating out of solution as iron oxides. For millions of years, this process continued in relative equilibrium. Cyanobacteria produced oxygen through photosynthesis, but that oxygen was immediately consumed by chemical reactions with the abundant reduced compounds in their environment. The atmospheric composition remained essentially unchanged, dominated by nitrogen, carbon dioxide, and methane, with virtually no free oxygen present. But cyanobacteria possessed a crucial evolutionary advantage that would ultimately prove decisive. Unlike the organisms that relied on scarce chemical electron donors, cyanobacteria had access to an essentially unlimited fuel source in the form of water. This allowed them to multiply and spread throughout the oceans at an unprecedented rate. As their populations grew, so did their collective production of oxygen. The cyanobacteria were not aware that they were conducting one of the greatest experiments in planetary engineering that Earth had ever witnessed. They were simply following their evolutionary programming, using sunlight and water to produce the energy and organic compounds they needed for growth and reproduction. But their success was setting the stage for a catastrophe that would reshape the entire planet. As cyanobacteria populations expanded across the ancient oceans, they began to form vast microbial mats in shallow coastal waters where sunlight could penetrate to support photosynthesis. These mats, some of which have been preserved as fossils, called stromatolites, were the visible sign of a biological revolution that was quietly transforming ocean chemistry on a global scale. The oxygen produced by these expanding cyanobacteria populations gradually began to overwhelm the ocean's capacity to consume it through chemical reactions with dissolved iron and sulfur compounds. For perhaps 200 million years, this process continued, with oxygen production slowly but steadily increasing as cyanobacteria populations grew and diversified throughout the world's oceans. The first signs of this impending transformation were recorded in the chemistry of ancient seafloor sediments. As dissolved iron in the oceans reacted with the increasing levels of oxygen produced by cyanobacteria, it precipitated out of solution and accumulated on the ocean floor in alternating bands of iron-rich and iron-poor sediments. These distinctive geological formations, known as banded iron formations, provide a detailed record of the gradual increase in oxygen production that preceded the great catastrophe to come. The banded iron formations tell a story of episodic oxygen release, with periods of high oxygen production alternating with periods of lower production, creating the characteristic striped appearance of these ancient rocks. Each band represents thousands of years of chemical precipitation, recording the slow but inexorable rise in oxygen levels that was occurring in the world's oceans. As this process continued over millions of years, something unprecedented in Earth's history was about to occur. The oxygen-consuming capacity of the oceans was approaching its limit. Iron concentrations were declining as more and more dissolved iron was converted to insoluble iron oxides and removed from the water column. Sulfur compounds were becoming increasingly oxidized, organic compounds in the water were being consumed by reactions with the growing concentrations of dissolved oxygen. The stage was being set for a transformation so profound, so catastrophic, that it would fundamentally alter every aspect of Earth's environment and drive the vast majority of life on the planet to extinction. The age of oxygen was about to begin, and with it, the greatest environmental catastrophe in Earth's history. But this catastrophe would also create the conditions necessary for the evolution of complex life, including, eventually, ourselves. The poisonous oxygen that would kill the ancient anaerobic biosphere would become the foundation for all aerobic life, from the smallest bacteria to the largest mammals. This is the profound paradox at the heart of our planet's history, that life's greatest innovation became life's greatest destroyer, and from that destruction arose all the complexity and beauty of the modern world. The transformation was beginning imperceptibly at first, but with gathering momentum that would reshape not just the chemistry of oceans and atmosphere, but the very nature of life itself on planet Earth. As we drift deeper into this ancient story, we must pause to consider the profound timescales over which these changes unfolded. The transformation of Earth's atmosphere was not a sudden catastrophe, but rather a gradual shift that occurred over hundreds of millions of years. To truly comprehend this process, we must adjust our perception of time itself, expanding our awareness to encompass geological epochs that dwarf all of human history. 2.4 billion years ago, as cyanobacteria continued their silent revolution in the world's oceans, the accumulated oxygen began to reach a critical threshold. The vast reserves of dissolved iron that had consumed oxygen for millions of years were becoming depleted. The chemical buffers that had maintained Earth's anaerobic atmosphere for over 1 billion years were approaching exhaustion. The planet was about to cross a point of no return. The transition began in the oceans themselves, where the chemistry of seawater underwent a fundamental transformation. For eons, the ancient seas had been a rich broth of dissolved metals and reduced compounds. Iron concentrations had been thousands of times higher than anything we observe in modern oceans. Sulfur compounds existed in forms that are virtually unknown in today's oxidized marine environment. The water itself would have appeared murky and discolored, tinted with the reds and oranges of dissolved iron and the yellows and greens of sulfur-bearing minerals. As oxygen levels continued to rise, this ancient chemistry began to break down. The dissolved iron that had given the oceans their distinctive coloration started to precipitate out of solution in vast quantities. This process created some of the most spectacular geological formations in Earth's history. Massive deposits of iron oxides that accumulated on seafloors around the world. These banded iron formations, with their distinctive alternating layers of iron-rich and iron-poor sediments, preserve a detailed record of the ocean's chemical transformation. Each band in these ancient rock formations represents a cycle of oxygen production and consumption that played out over thousands of years. The iron-rich layers formed during periods when cyanobacteria were producing large amounts of oxygen, causing dissolved iron to precipitate rapidly from seawater. The iron-poor layers formed during intervals when oxygen production was lower, allowing other chemical processes to dominate seafloor sedimentation. The formation of these iron deposits represented more than just a change in ocean chemistry. It marked the removal of one of the most important nutrients available to early life forms. Many of the anaerobic organisms that had dominated the ancient biosphere depended on iron compounds for their metabolic processes. As dissolved iron became increasingly scarce, these organisms faced a growing crisis that would ultimately threaten their very survival. The depletion of dissolved iron also had profound effects on the global nitrogen cycle. Iron-based enzymes played crucial roles in the biological processes that converted atmospheric nitrogen into forms that could be used by living organisms. As bioavailable iron became scarce, the efficiency of nitrogen fixation declined, creating additional stress on the already challenged anaerobic ecosystems. But the chemical transformation of the oceans extended far beyond the precipitation of iron. Sulfur compounds, which had provided energy for countless generations of sulfur-reducing bacteria, began to undergo oxidation reactions that fundamentally altered their chemical behavior. Hydrogen sulfide, once abundant in ancient seawater, reacted with increasing levels of dissolved oxygen to form sulfate compounds that many anaerobic organisms could not utilize for their metabolisms. The changing chemistry of the oceans created a cascade of effects that rippled through every level of the marine ecosystem. Organisms that had evolved over hundreds of millions of years to thrive in the reduced chemical environment of the ancient seas suddenly found their world becoming increasingly hostile. The very compounds that had sustained their metabolisms for countless generations were being transformed into chemical forms they could not use. As the oceans continued their chemical evolution, the effects began to extend beyond the marine environment itself. The interaction between seawater and the atmosphere became increasingly dominated by oxygen-producing and oxygen-consuming processes. The ancient equilibrium that had maintained stable atmospheric composition for over 1 billion years was beginning to break down. The atmosphere of the early Earth had been maintained in its oxygen-free state, not just by biological processes, but by a complex web of chemical reactions involving volcanic gases, surface minerals, and atmospheric photochemistry. Methane, the dominant greenhouse gas of the ancient atmosphere, was particularly vulnerable to the rising levels of oxygen. When oxygen molecules encountered methane in the upper atmosphere, they initiated a series of chemical reactions that broke down the methane molecules and converted them to carbon dioxide and water vapor. This process had profound implications for Earth's climate system. Methane is an extremely potent greenhouse gas, approximately 25 times more effective at trapping heat than carbon dioxide. The destruction of atmospheric methane by rising oxygen levels began to weaken the greenhouse effect that had kept the planet warm for billions of years. As methane concentrations declined, global temperatures started to drop, initiating a cooling trend that would eventually lead to one of the most severe ice ages in Earth's history. The chemical reactions between oxygen and methane also produced water vapor, which further complicated the atmospheric chemistry of the transitioning planet. Water vapor in the upper atmosphere could undergo photochemical reactions that produced additional reactive compounds, creating a complex web of atmospheric chemistry that was unlike anything that had existed in Earth's previous history. As these atmospheric changes accelerated, they began to affect the surface chemistry of the planet in unprecedented ways. The interaction between the oxygen-rich atmosphere and surface minerals initiated weathering processes that had been impossible under the reducing conditions of the ancient world. Iron-bearing minerals in exposed rocks began to oxidize, forming the distinctive red iron oxides that would later give the planet's deserts their characteristic coloration. These weathering processes represented more than just cosmetic changes to the planet's appearance. The oxidation of surface minerals consumed significant quantities of atmospheric oxygen, helping to regulate the rate at which oxygen levels continue to rise. This created a complex feedback system where rising oxygen levels accelerated chemical weathering, which in turn consumed oxygen and moderated the rate of atmospheric change. The transformation of surface chemistry also affected the global carbon cycle in ways that would have far-reaching consequences for the planet's climate system. The oxidation of organic compounds in soils and sediments released carbon dioxide into the atmosphere, partially offsetting the cooling effect of methane destruction. However, the overall trend was toward a cooler, more chemically reactive planet, where oxygen played an increasingly dominant role in atmospheric and surface processes. As oxygen levels continued to rise, they eventually reached concentrations sufficient to support the formation of an ozone layer in the upper atmosphere. This development marked a crucial turning point in the planet's environmental history. For billions of years, ultraviolet radiation from the sun had penetrated deep into Earth's atmosphere, reaching the surface with an intensity that would have been lethal to most forms of life we know today. The formation of the ozone layer created a protective shield that filtered out the most harmful ultraviolet radiation before it could reach the planet's surface. This had immediate effects on atmospheric photochemistry, altering the rates of chemical reactions that had previously been driven by high-energy ultraviolet light. The reduced ultraviolet flux also affected the stability of atmospheric gases, allowing oxygen concentrations to continue rising without being broken down by photochemical processes. The emergence of the ozone layer can be detected in the geological record through subtle changes in the isotopic composition of sulfur compounds preserved in ancient rocks. Under the high ultraviolet conditions that prevailed before the formation of the ozone layer, sulfur isotopes underwent mass-independent fractionation processes that created distinctive chemical signatures. The disappearance of these signatures from the geological record marks the point at which the ozone layer became sufficiently developed to shield the lower atmosphere from intense ultraviolet radiation. With the establishment of an ozone layer, Earth's atmosphere entered a new phase of stability that would persist for billions of years. The presence of free oxygen and the protective ozone shield created conditions that were fundamentally different from anything that had existed in the planet's previous history. These new atmospheric conditions would eventually make possible the evolution of complex multicellular life, but their immediate effect was to create an environmental crisis that threatened the very existence of the anaerobic organisms that had dominated Earth's biosphere for over 1 billion years. The rising levels of atmospheric oxygen represented a direct threat to the cellular machinery of anaerobic life forms. Oxygen is an extremely reactive molecule that can damage the delicate organic compounds that form the basis of cellular structures and metabolic processes. The proteins, lipids, and genetic material of anaerobic organisms had evolved in the complete absence of oxygen, and they lacked the protective mechanisms necessary to prevent oxidative damage. When oxygen molecules penetrated the cells of anaerobic organisms, they initiated a cascade of chemical reactions that could destroy essential cellular components. The oxidation of sulfur-containing amino acids could disrupt protein structure and function. The reaction of oxygen with unsaturated fatty acids could damage cell membranes, compromising the ability of cells to maintain their internal chemical environment. Most critically, oxygen could react with the genetic material itself, causing mutations that could be fatal to the organisms. The toxicity of oxygen was not just a matter of direct chemical damage to cellular components. The presence of oxygen also disrupted the metabolic pathways that anaerobic organisms had relied upon for energy production. Many of these organisms used enzyme systems that were specifically adapted to function in the absence of oxygen. The introduction of oxygen into their cellular environment could interfere with these enzymes, making it impossible for the organisms to generate the energy they needed for survival. For organisms that had evolved over hundreds of millions of years in an oxygen-free environment, the rising levels of atmospheric oxygen represented an unprecedented environmental challenge. Unlike other forms of environmental stress, such as changes in temperature or nutrient availability, the introduction of oxygen into their world was not something that could be adapted to through minor evolutionary adjustments. The fundamental incompatibility between anaerobic metabolism and oxygen-rich environments meant that most of these ancient life forms faced a stark choice: evolve completely new metabolic systems or face extinction. The response of the anaerobic biosphere to rising oxygen levels was not uniform across all organisms. Some species were more vulnerable than others, depending on their specific metabolic pathways and cellular structures. The methanogens, which had been among the most successful organisms in the ancient biosphere, were particularly susceptible to oxygen toxicity. Their metabolic processes were not only disrupted by the presence of oxygen, but the destruction of atmospheric methane by oxygen also eliminated the chemical environment that had allowed them to thrive. Other anaerobic organisms showed varying degrees of resistance to oxygen exposure. Some sulfur-reducing bacteria possessed cellular mechanisms that provided limited protection against oxidative damage, allowing them to survive in environments with low but detectable levels of oxygen. Some iron-reducing bacteria were able to retreat to deeper, more oxygen-poor environments where they could continue their ancient metabolic processes. The differential survival of anaerobic organisms created a complex pattern of extinction and persistence that played out over millions of years. The most oxygen-sensitive species were the first to disappear from the fossil record, while more resistant forms managed to persist in increasingly restricted environmental niches. This gradual winnowing of the anaerobic biosphere represented one of the most profound biological transformations in Earth's history. As the Great Oxidation Event continued to unfold, its effects extended far beyond the direct toxicity of oxygen to anaerobic life forms. The changing chemistry of the atmosphere and oceans created a cascade of environmental changes that affected every aspect of the planet's biosphere. The destruction of atmospheric methane not only eliminated the greenhouse effect that had maintained warm global temperatures, but also removed a chemical environment that had been essential for many forms of anaerobic metabolism. The cooling that resulted from the loss of methane's greenhouse effect was gradual at first, but it accelerated as oxygen levels continued to rise and methane concentrations declined. Global temperatures began to drop toward levels that had not been experienced since the earliest days of Earth's history. The warm, humid conditions that had characterized the planet for over 1 billion years gave way to a cooler, more variable climate system. This climatic transformation had profound effects on the distribution and abundance of life on Earth. Many organisms that had been adapted to the stable, warm conditions of the ancient world found themselves unable to cope with the increasing temperature variability. The cooling trend also affected the chemistry of the oceans, altering the solubility of gases and minerals in ways that further disrupted marine ecosystems. The changes in ocean chemistry were particularly significant for organisms that depended on dissolved nutrients for their survival. As temperatures dropped, the solubility of many essential minerals increased, but the biological availability of these nutrients was often reduced by the changing chemical environment. The formation of new mineral phases in response to increasing oxygen levels could trap nutrients in forms that many organisms could not access. The combination of direct oxygen toxicity, changing nutrient availability, and climatic cooling created a perfect storm of environmental stress that challenged every aspect of the ancient biosphere. The organisms that had dominated Earth's ecosystems for over 1 billion years found themselves facing multiple, simultaneous threats that tested the limits of their evolutionary adaptability. As the environmental crisis deepened, the geographical distribution of life on Earth began to change dramatically. Areas that had previously supported thriving communities of anaerobic organisms became increasingly hostile to their survival. The shallow marine environments where cyanobacteria were most active became particularly dangerous for oxygen-sensitive species, forcing many organisms to retreat to deeper, more chemically reducing environments. The deep ocean basins, where oxygen levels remained low due to limited mixing with surface waters, became refugia for many anaerobic species. The sediments of the deep sea floor, rich in organic matter and isolated from atmospheric oxygen, provided environments where ancient metabolic processes could continue to operate. Hot springs and hydrothermal vents, with their chemically reducing waters and abundant energy sources, became oases of anaerobic life in an increasingly oxidized world. But even these refugia were not completely immune to the effects of the Great Oxidation Event. The changing chemistry of seawater gradually affected even the deepest ocean basins, as oxygen-rich surface waters slowly mixed with the deeper layers. The global circulation patterns that transported nutrients and gases throughout the ocean system ensured that no part of the marine environment remained completely unaffected by the atmospheric transformation taking place above. The retreat of anaerobic life to increasingly restricted environments represented more than just a geographical redistribution of organisms. It marked the end of an era in which anaerobic metabolism had been the dominant form of energy production on Earth. For over 1 billion years, the planet's biosphere had been powered primarily by chemical reactions that did not require oxygen. The rise of oxygen marked the beginning of a transition toward aerobic metabolism that would eventually become the foundation of all complex life. This transition was not immediate, nor was it complete. Even today, billions of years after the Great Oxidation Event, anaerobic organisms continue to play important roles in many ecosystems. The deep subsurface of the Earth, the sediments of lakes and oceans, and the digestive systems of many animals still harbour communities of organisms that operate using the ancient metabolic pathways that once dominated the planet. But the scope and influence of anaerobic life was forever changed by the Great Oxidation Event. What had once been the primary form of metabolism on Earth became relegated to specialized niches where oxygen could not penetrate. The chemical transformation of the atmosphere and oceans had fundamentally altered the rules of biological existence, creating new opportunities for some forms of life while closing off ancient pathways that had sustained the biosphere for eons. As we contemplate this vast transformation, we must remember that it unfolded over timescales that challenge human comprehension. The Great Oxidation Event was not a sudden catastrophe that occurred over years or even millennia, but rather a gradual process that extended over hundreds of millions of years. Individual organisms lived and died countless times as the chemical composition of their world slowly shifted around them. The geological record preserves evidence of this gradual transformation in layers of rock that accumulated grain by grain over unimaginable spans of time. Each stratum tells a part of the story, recording subtle changes in ocean chemistry, atmospheric composition, and biological activity that marked the planet's transition from an anaerobic to an aerobic world. The banded iron formations that record the initial phases of oceanic oxygenation extend through rock sequences that represent millions of years of deposition. The gradual disappearance of mass-independent sulfur isotope fractionation from the geological record marks a transition that occurred over tens of millions of years as the ozone layer slowly developed. The changes in carbon isotope ratios that reflect the transformation of the global carbon cycle played out over time periods that encompass the rise and fall of entire evolutionary lineages. This deep time perspective is essential for understanding the true significance of the Great Oxidation Event. It was not simply a biological crisis that affected individual organisms or species, but rather a planetary transformation that reshaped the fundamental chemical and physical processes that govern life on Earth. The changes that occurred during this period established the environmental conditions that would persist for billions of years, creating the chemical foundation upon which all subsequent evolution would build. The legacy of the Great Oxidation Event extends far beyond the extinction of anaerobic organisms and the establishment of oxygen-rich atmospheric conditions. The chemical transformation of the planet during this period created new possibilities for biological innovation that had been impossible under the reducing conditions of the ancient world. The availability of oxygen as a powerful oxidizing agent opened up new metabolic pathways that could extract far more energy from organic compounds than had been possible using anaerobic processes. The development of aerobic respiration, the metabolic process that powers most complex life today, was made possible by the oxygen-rich environment created by the Great Oxidation Event. This highly efficient form of energy production would eventually enable the evolution of multicellular organisms with the energy budgets necessary to support complex body plans, active lifestyles, and sophisticated behavioral repertoires. The formation of the ozone layer also created new possibilities for life on Earth's surface. For billions of years, the land had been essentially sterile, bathed in lethal levels of ultraviolet radiation that prevented any form of life from establishing itself outside the protective waters of the oceans. The ozone shield created by rising oxygen levels would eventually make possible the colonization of terrestrial environments, opening up vast new habitats for evolutionary exploration. But these future possibilities were not apparent to the organisms living through the Great Oxidation Event itself. For them, the rising levels of oxygen represented an immediate and existential threat that challenged their very survival. The environmental crisis they faced was as severe as any that has occurred in Earth's history, threatening to eliminate forms of life that had dominated the planet for over 1 billion years. The response of different organisms to this crisis varied enormously, creating a complex mosaic of extinction, survival, and adaptation that played out over millions of years. Some lineages disappeared entirely from the fossil record, unable to cope with the changing chemical environment. Others managed to persist in increasingly restricted refugia, maintaining ancient metabolic traditions in isolated pockets of the biosphere. A few organisms managed to adapt to the changing conditions, developing new metabolic capabilities that allowed them to not only tolerate oxygen, but actually use it for their own benefit. These evolutionary pioneers would become the ancestors of all aerobic life, from the bacteria that decompose organic matter to the animals that depend on oxygen for their survival. The story of these adaptations represents one of the most remarkable chapters in evolutionary history. The transition from anaerobic to aerobic metabolism required fundamental changes in cellular biochemistry, involving the evolution of new enzyme systems, protective mechanisms against oxidative damage, and entirely new metabolic pathways. The organisms that achieved these adaptations gained access to energy sources that were far more abundant and efficient than anything available through anaerobic processes. The cyanobacteria themselves, the organisms whose photosynthetic activities had initiated the Great Oxidation Event, faced their own challenges during this period. While they were responsible for producing the oxygen that was transforming the planet, they too had to adapt to the increasingly oxidized environment they were creating. The early cyanobacteria had evolved in a world where oxygen levels were low, and the rising concentrations of their own metabolic product posed challenges for their continued survival and growth. The success of cyanobacteria in adapting to high oxygen conditions was crucial for the continued transformation of Earth's atmosphere. These organisms not only had to tolerate the oxygen they produced, but they also had to develop mechanisms for protecting themselves against the reactive oxygen species that could damage their cellular machinery. The evolution of antioxidant systems and repair mechanisms in cyanobacteria was essential for maintaining the photosynthetic processes that continue to drive atmospheric oxygenation. As cyanobacteria populations adapted to high oxygen conditions, they were able to expand into new environments and ecological niches. Their ability to produce oxygen through photosynthesis gave them a competitive advantage in the changing world, allowing them to outcompete many of the anaerobic organisms that had previously dominated marine ecosystems. The success of cyanobacteria accelerated the pace of atmospheric transformation, creating a positive feedback loop that drove oxygen levels even higher. The expansion of cyanobacteria populations also had important effects on ocean productivity and nutrient cycling. These organisms were highly efficient at converting carbon dioxide and nutrients into organic matter, supporting food webs that could sustain higher levels of biological activity than had been possible under purely anaerobic conditions. The increased productivity of marine ecosystems helped to drive further changes in ocean chemistry as organic matter production and decomposition processes became increasingly important in regulating the chemical composition of seawater. The transformation of marine ecosystems during the Great Oxidation Event represented a fundamental shift in the way that energy and materials flowed through the biosphere. The dominance of oxygen-producing photosynthesis as the primary form of energy capture marked the beginning of modern-style ecosystem functioning, where the vast majority of biological activity is ultimately powered by sunlight and oxygen-based metabolism. This ecosystem transformation had profound effects on the global cycles of carbon, nitrogen, sulfur, and other essential elements. The oxidation of organic matter by oxygen-breathing organisms created new pathways for the recycling of nutrients, while the formation of oxidized minerals on land and in the oceans established new reservoirs for the storage of chemical elements. These changes in biogeochemical cycling would have lasting effects on the composition of the atmosphere and oceans, establishing chemical patterns that persist to this day. As we follow this vast narrative through deep time, we begin to see how the Great Oxidation Event was not simply a crisis that life survived, but rather a transformation that created the environmental conditions necessary for the evolution of complexity and diversity that characterizes the modern biosphere. The oxygen that was initially toxic to most life became the foundation for metabolic processes that could support larger, more active, and more complex organisms than had ever existed before. The story continues to unfold through geological time as the chemical and biological changes initiated by the Great Oxidation Event rippled through Earth's systems for hundreds of millions of years. The planet that emerged from this transformation was fundamentally different from the world that had existed for the first 2 billion years of Earth's history, set on a trajectory toward the evolution of multicellular life, complex ecosystems, and eventually the emergence of intelligence itself. The transformation we have witnessed thus far was merely the beginning of a cascade of changes that would reshape every aspect of our planet's existence. As oxygen continued its inexorable rise through the ancient atmosphere, the chemical reactions it initiated grew ever more complex and far-reaching. The simple molecule that had once been nothing more than a waste product of photosynthesis was becoming the architect of an entirely new Earth. The chemistry of this transformation unfolded across multiple timescales simultaneously. At the molecular level, individual oxygen atoms collided with methane molecules in reactions that lasted mere fractions of a second. At the geological level, these countless billions of microscopic reactions accumulated over millions of years to produce changes in atmospheric composition that would persist for eons. Understanding this transformation requires us to appreciate both the immediate violence of oxidation reactions and the patient persistence of geological time. In the upper reaches of the ancient atmosphere, where ultraviolet radiation from the sun was most intense, oxygen molecules encountered methane in concentrations that had been stable for over 1 billion years. The collision between these molecules initiated a complex series of chemical reactions that would fundamentally alter the planet's energy balance. Methane, with its 4 hydrogen atoms bound to a central carbon, was particularly vulnerable to attack by the highly reactive oxygen. When oxygen encountered methane in the presence of ultraviolet light, the reaction proceeded through a series of intermediate steps that broke apart the methane molecule piece by piece. First, a hydrogen atom would be stripped away, creating a methyl radical that was even more reactive than the original methane. This methyl radical would then react with additional oxygen molecules, ultimately producing carbon dioxide and water vapor as the final products of the reaction. The conversion of methane to carbon dioxide had profound implications for Earth's climate system. While carbon dioxide is indeed a greenhouse gas, its warming effect is much weaker than that of methane. The molecule-by-molecule replacement of methane with carbon dioxide represented a gradual weakening of the greenhouse effect that had maintained Earth's warm climate for billions of years. As this process continued over millions of years, global temperatures began a slow but steady decline. The water vapor produced by methane oxidation added another layer of complexity to the changing atmospheric system. In the cold upper atmosphere, much of this water vapor condensed into ice crystals that reflected sunlight back into space, contributing to the cooling trend. However, water vapor in the lower atmosphere continued to act as a greenhouse gas, partially offsetting the loss of methane's warming effect. The balance between these competing effects determined the rate at which global temperatures declined. The destruction of atmospheric methane also had important consequences for the organisms that had produced it in the first place. Methanogens had maintained their dominance in the ancient biosphere, partly because the methane they produced helped maintain the warm, stable climate that favoured their growth and reproduction. As methane levels declined and temperatures began to drop, the environmental conditions that had allowed methanogens to thrive for billions of years started to deteriorate. The cooling trend initiated by methane destruction was gradual at first, measurable only over periods of millions of years. But as oxygen levels continued to rise and methane concentrations continued to fall, the rate of cooling began to accelerate. The planet's climate system was approaching a threshold beyond which the changes would become irreversible and catastrophic. The effects of atmospheric cooling were first felt in the polar regions, where ice began to form for the first time in Earth's history. Initially, this ice was confined to small areas at the very highest latitudes, but as cooling continued, the ice sheets began to expand toward the equator. The formation of ice created a powerful positive feedback mechanism that accelerated the cooling process. Ice is highly reflective, bouncing most of the sunlight that strikes it back into space rather than absorbing it as heat. As more of Earth's surface became covered with ice, less solar energy was absorbed by the planet, causing temperatures to drop even further. This additional cooling led to the formation of more ice, which reflected even more sunlight and caused still more cooling. The process became self-reinforcing, driving the planet toward a climatic state unlike anything it had experienced since the earliest days of its formation. The expansion of ice sheets had immediate effects on global ocean circulation patterns. The formation of ice at high latitudes created temperature gradients that drove new patterns of ocean currents, transporting cold water from polar regions toward the equator and warm water from equatorial regions toward the poles. These circulation changes affected the distribution of nutrients and dissolved gases throughout the ocean system, further disrupting marine ecosystems that were already struggling with rising oxygen levels. As ice sheets continued to expand, they began to affect the global water cycle in ways that amplified the cooling trend. Water that had previously evaporated from the oceans and returned as rain was now being trapped in the growing ice sheets, reducing the amount of water vapor in the atmosphere. Since water vapor is itself a potent greenhouse gas, this reduction further weakened the planet's ability to retain heat from the sun. The growing ice sheets also affected sea level, causing it to drop as more and more water became locked up in glacial ice. This sea level decline exposed coastal areas that had been underwater for millions of years, creating new land surfaces that were immediately subjected to chemical weathering by the increasingly oxygen-rich atmosphere. The weathering of these newly exposed rocks consumed additional oxygen from the atmosphere while releasing carbon dioxide, creating complex feedback loops that influence both atmospheric composition and global climate. The chemical weathering processes initiated by exposure to oxygen-rich air were unlike anything that had occurred during Earth's anaerobic past. Iron-bearing minerals that had been stable under reducing conditions began to oxidize rapidly when exposed to atmospheric oxygen, forming the distinctive red iron oxides that would eventually give many of Earth's landscapes their characteristic coloration. This oxidation process consumed vast quantities of atmospheric oxygen, temporarily slowing the rate at which oxygen levels continued to rise. The weathering of sulfur-bearing minerals created additional complications for the changing atmospheric system. When these minerals were exposed to oxygen and water, they formed sulfuric acid compounds that could dramatically lower the pH of rainwater and surface waters. This acidification had immediate effects on any remaining life forms in freshwater environments, creating yet another source of stress for organisms that were already struggling with the toxic effects of rising oxygen levels. As the ice sheets continued their relentless expansion toward the equator, the planet entered a climatic state that geologists have termed snowball Earth. By approximately 2 billion years ago, ice extended from the polar regions all the way to the tropics, creating a frozen world where average global temperatures may have dropped to -40 degrees Celsius or lower. Even at the equator, where solar energy input was at its maximum, ice sheets several kilometers thick covered both land and ocean. The snowball Earth conditions created by the Great Oxidation Event represented one of the most extreme climatic states in Earth's history. The ice-covered planet reflected so much sunlight back into space that very little solar energy was absorbed at the surface. Ocean circulation virtually ceased as the seas froze to depths of more than a kilometer. The water cycle ground to a halt as virtually all atmospheric moisture became locked up in the global ice sheet. Under these extreme conditions, the few remaining pockets of life on Earth were forced to retreat to the most marginal of environments. Hydrothermal vents on the ocean floor, where volcanic heat could maintain small areas of liquid water beneath the global ice sheet, became oases of life in an otherwise frozen world. Hot springs on land, where geothermal energy could melt the overlying ice, provided tiny refugia where some organisms could survive. The organisms that survived in these extreme environments were predominantly anaerobic species that had already adapted to oxygen-free conditions. The global ice cover actually provided some protection from the toxic effects of atmospheric oxygen, since the ice prevented the gas from dissolving into the small pockets of liquid water where life persisted. In a cruel irony, the climatic catastrophe caused by rising oxygen levels created conditions that temporarily favored the very organisms that oxygen was destroying. The snowball Earth state persisted for hundreds of millions of years, from approximately 2.3 billion years ago to about 2 billion years ago. During this time, the planet remained locked in a frozen state that prevented most biological activity and dramatically slowed the processes of atmospheric and oceanic change. The ice-covered oceans could no longer support the photosynthetic activity of cyanobacteria, causing oxygen production to decline to very low levels. However, the volcanic activity that continued beneath the global ice sheet gradually began to tip the balance back toward a warmer climate. Volcanoes continued to emit carbon dioxide into the atmosphere throughout the snowball Earth period. And with photosynthesis virtually shut down, there was no biological process removing this carbon dioxide from the air. Over millions of years, volcanic carbon dioxide slowly accumulated in the atmosphere until its greenhouse effect became strong enough to begin melting the global ice sheet. The emergence from snowball Earth conditions was as dramatic as the entry into them had been. Once the ice sheets began to retreat, the process accelerated rapidly due to the same feedback mechanisms that had driven the initial cooling. As ice melted and exposed dark land and ocean surfaces, more solar energy was absorbed, causing additional warming and more ice melting. The planet transitioned from a completely frozen state to a warm, ice-free world in a relatively brief geological interval. The end of the snowball Earth period marked the beginning of a new phase in Earth's atmospheric evolution. The massive accumulation of volcanic carbon dioxide during the frozen period created a super greenhouse effect that drove global temperatures to levels higher than they had been before the onset of glaciation. This warming phase lasted for millions of years, gradually moderating as the excess carbon dioxide was removed from the atmosphere through chemical weathering and renewed biological activity. The climatic oscillation between snowball Earth and super greenhouse conditions demonstrated the sensitivity of the planet's climate system to changes in atmospheric composition. The relatively small changes in greenhouse gas concentrations that had initiated the cooling trend had triggered a cascade of feedbacks that drove the climate to an extreme state. Similarly, the gradual accumulation of volcanic carbon dioxide during the frozen period had eventually triggered feedbacks that drove the climate to the opposite extreme. These dramatic climatic changes had profound effects on the evolution of life during the Great Oxidation Event. The organisms that survived the snowball Earth period were those that had been able to tolerate not only the toxic effects of oxygen, but also the extreme cold and limited resources of the frozen world. The selective pressures imposed by these harsh conditions favored organisms with robust metabolisms and the ability to survive in dormant states for extended periods. The warming period that followed the end of Snowball Earth created new opportunities for evolutionary innovation. The retreat of the ice sheets exposed vast areas of land and shallow ocean that had been frozen for hundreds of millions of years. These newly available habitats provided space for the expansion and diversification of the organisms that had survived the climatic catastrophe. The cyanobacteria were among the first organisms to take advantage of the improving conditions. As liquid water became available again and sunlight could reach the ocean surface, photosynthetic activity resumed on a global scale. However, the cyanobacteria that emerged from the Snowball Earth period were different from their ancestors. The extreme selective pressures of the frozen world had favored variants that were more tolerant of cold conditions and more efficient at photosynthesis under low-light conditions. The resumption of large-scale photosynthesis after the Snowball Earth period initiated a new phase of atmospheric oxygenation. However, the rate of oxygen production during this period was moderated by several factors that had not been present during the initial rise of oxygen levels. The chemical weathering processes that had been accelerated during the warming period consumed significant quantities of atmospheric oxygen, preventing oxygen levels from rising as rapidly as they had before the glaciation. The ocean chemistry that emerged after the Snowball Earth period was also significantly different from the conditions that had prevailed during the early stages of the Great Oxidation event. The massive precipitation of iron during the initial oxygenation had removed most of the dissolved iron from seawater, eliminating one of the major chemical buffers that had previously consumed oxygen. This meant that any oxygen produced by photosynthesis after the Snowball Earth period could accumulate more rapidly in both seawater and the atmosphere. The post-Snowball Earth period was characterized by a complex interplay between biological, chemical, and physical processes that gradually established the atmospheric and oceanic conditions that would persist for the remainder of Earth's history. Oxygen levels continued to rise, but at a more measured pace that allowed some degree of adaptation by the surviving life forms. The climate system gradually stabilized at intermediate conditions that were neither as warm as the pre-Snowball Earth world, nor as cold as the frozen period. The establishment of stable oxygen-rich atmospheric conditions during this period marked a fundamental turning point in Earth's history. For the first time since the origin of life, the planet's atmosphere contained significant quantities of free oxygen that could support new types of metabolic processes. The stage was set for the evolution of aerobic respiration, the highly efficient energy-producing process that would eventually power all complex multicellular life. The development of aerobic respiration was not an immediate consequence of rising oxygen levels, but rather a gradual evolutionary process that unfolded over millions of years. The first organisms to develop the ability to use oxygen for energy production were likely bacteria that had previously relied on anaerobic metabolic processes. These pioneering aerobic bacteria gained access to a much more efficient method of extracting energy from organic compounds, giving them a significant competitive advantage over their anaerobic relatives. The evolution of aerobic respiration represented a fundamental breakthrough in biological energy production. Anaerobic metabolic processes could extract only a small fraction of the energy available in organic compounds, limiting the size and complexity of the organisms that depended on these processes. Aerobic respiration, in contrast, could extract nearly 20 times more energy from the same organic compounds, providing the energy budget necessary to support larger, more active, and more complex life forms. The availability of oxygen for energy production also enabled the evolution of new biosynthetic pathways that required the oxidizing power of oxygen. Many of the complex organic molecules that are essential for advanced cellular functions, including sterols and other membrane components, can only be synthesized in the presence of oxygen. The evolution of these biosynthetic capabilities was a prerequisite for the development of the more sophisticated cellular structures that would eventually characterize eukaryotic cells. The transition from an anaerobic to an aerobic biosphere was not simply a matter of replacing one set of organisms with another. Instead, it involved the gradual integration of aerobic and anaerobic processes within the same ecosystems and even within the same organisms. Many of the bacteria that survived the Great Oxidation Event developed the ability to switch between aerobic and anaerobic metabolism, depending on the availability of oxygen in their environment. This metabolic flexibility proved to be crucial for survival in a world where oxygen levels were still highly variable and unpredictable. The atmosphere and oceans of the post-snowball Earth period experienced significant fluctuations in oxygen concentration as the global biogeochemical cycles adjusted to the new chemical conditions. Organisms that could adapt their metabolism to these changing conditions were much more likely to survive and reproduce than those that were locked into a single metabolic strategy. The development of metabolic flexibility also had important consequences for the evolution of multicellular life. The ability to function under both aerobic and anaerobic conditions allowed organisms to explore new environmental niches where oxygen levels might be variable or limited. This metabolic versatility would eventually prove essential for the evolution of complex multicellular organisms, many of which contain specialized tissues that function under different oxygen concentrations. As oxygen levels continued to stabilize and rise during the post-snowball Earth period, the chemical composition of the atmosphere began to approach values that would be recognizable to modern observers. By approximately 1.8 billion years ago, oxygen concentrations had reached levels that could support the formation of a stable ozone layer in the upper atmosphere. This ozone layer provided crucial protection against the harmful ultraviolet radiation that had previously sterilized most of Earth's surface. The formation of a stable ozone layer marked another critical milestone in Earth's atmospheric evolution. For the first time in the planet's history, the surface environment was protected from the most damaging forms of solar radiation, making it possible for life to begin exploring terrestrial habitats. However, the colonization of land by living organisms would not occur for hundreds of millions of years, as the evolution of the complex cellular and biochemical machinery necessary for terrestrial life required extensive evolutionary innovation. The ozone layer also had important effects on atmospheric chemistry and climate. The absorption of ultraviolet radiation by ozone converted that energy into heat, warming the upper atmosphere and creating temperature gradients that influence global circulation patterns. The presence of ozone also affected the rates of photochemical reactions in the atmosphere, altering the production and destruction rates of various trace gases that influence climate and air quality. The establishment of an ozone-protected atmosphere created feedback loops that helped stabilize oxygen concentrations at levels that could sustain complex life. The reduced ultraviolet flux at Earth's surface decreased the rate at which oxygen was broken down by photochemical processes, allowing oxygen to accumulate to higher concentrations than would have been possible under the high radiation conditions of the pre-ozone atmosphere. As the atmosphere continued its evolution toward modern composition, the oceans underwent equally dramatic transformations. The chemistry of seawater during the post-snowball Earth period was fundamentally different from either the reducing conditions of the early Archean oceans or the highly oxidized conditions of modern seawater. Instead, the oceans of this period were characterized by a complex stratification of chemical conditions that varied with depth and geographic location. Near the surface, where photosynthetic activity was highest, oxygen concentrations approached levels that could support aerobic life. However, in deeper waters, where sunlight could not penetrate and photosynthesis was impossible, oxygen levels remained low and anaerobic conditions persisted. This chemical stratification created a three-dimensional mosaic of environmental conditions that supported different types of organisms at different depths. The stratified ocean chemistry of this period had important consequences for the cycling of nutrients and other essential elements. In the oxygen-rich surface waters, organic matter was rapidly decomposed by aerobic bacteria, releasing nutrients back into the water column where they could support additional photosynthetic activity. However, in the oxygen-poor deep waters, organic matter accumulated in sediments where it was slowly decomposed by anaerobic processes. This differential decomposition created vertical gradients in nutrient concentration that influenced the productivity and species composition of marine ecosystems. Surface waters, where nutrients were rapidly recycled, could support high levels of photosynthetic activity, but were often limited by the availability of essential nutrients like nitrogen and phosphorus. Deep waters, where nutrients accumulated due to slow decomposition rates, contained high concentrations of dissolved nutrients but lacked the sunlight necessary to support photosynthesis. The establishment of these vertical gradients in ocean chemistry created the foundation for the complex marine ecosystems that would evolve over the following billions of years. The interaction between surface productivity and deep water nutrient storage became a fundamental organizing principle of marine ecology, influencing everything from the distribution of marine organisms to the global cycles of carbon and other essential elements. The chemical stratification of the oceans also had important effects on the continued evolution of atmospheric oxygen levels. The burial of organic matter in oxygen-poor deep water sediments represented a net removal of carbon from the ocean atmosphere system, which had to be balanced by the input of carbon from volcanic and weathering processes. This balance between organic carbon burial and inorganic carbon input became a major factor regulating atmospheric oxygen concentrations over geological timescales. As the Great Oxidation Event continued to unfold over hundreds of millions of years, the pace of change gradually began to slow. By approximately 1.5 billion years ago, the major chemical transformations of atmosphere and oceans had been largely completed. Oxygen levels had stabilized at concentrations that could support aerobic life. The ozone layer provided protection from harmful radiation, and ocean chemistry had established the stratified conditions that would characterize marine environments for the remainder of Earth's history. However, the establishment of these stable conditions did not mark the end of atmospheric evolution. Instead, it marked the beginning of a new phase of more subtle but equally important changes that would continue to shape Earth's environment for billions of years to come. The interactions between biological, chemical, and physical processes that had been established during the Great Oxidation Event created a complex web of feedbacks that would regulate atmospheric composition and climate over geological timescales. The legacy of the Great Oxidation Event extended far beyond the immediate changes in atmospheric and oceanic chemistry. The selective pressures imposed by rising oxygen levels had fundamentally altered the trajectory of biological evolution, favoring organisms with the biochemical machinery necessary to tolerate or utilize oxygen. These evolutionary changes created the foundation for all subsequent biological innovation, from the evolution of eukaryotic cells to the eventual development of complex multicellular life. The metabolic innovations that emerged during the Great Oxidation Event also established the energetic basis for the evolution of larger and more complex organisms. The highly efficient energy production made possible by aerobic respiration provided the power necessary to support active lifestyles, complex behaviors, and sophisticated cellular structures. Without these metabolic innovations, the evolution of animals, plants, and fungi as we know them would have been impossible. The atmospheric changes initiated by the Great Oxidation Event also created the environmental conditions necessary for the eventual colonization of terrestrial habitats. The ozone layer protection from ultraviolet radiation, the availability of oxygen for respiration, and the establishment of stable climate conditions all contributed to making land surfaces habitable for living organisms. The colonization of land would not occur for hundreds of millions of years, but the Great Oxidation Event established the prerequisite conditions that made this expansion possible. As we contemplate the vast scope of this transformation, we must appreciate the profound interconnectedness of Earth's biological, chemical, and physical systems. The Great Oxidation Event was not simply a biological phenomenon that affected living organisms, nor was it merely a chemical process that altered atmospheric composition. Instead, it was a complex system-level transformation that involved feedbacks and interactions between every component of the Earth system. The rise of oxygen demonstrates the capacity of life to reshape its own environment on a planetary scale. The photosynthetic innovations of cyanobacteria did not occur in isolation, but rather triggered a cascade of changes that affected every aspect of Earth's environment. The oxygen produced by these organisms altered atmospheric chemistry, ocean chemistry, climate, and the distribution and evolution of life itself. This system-level perspective is essential for understanding the true significance of the Great Oxidation Event. It was not simply an episode in Earth's history that can be understood in isolation, but rather a foundational transformation that established many of the basic characteristics of our modern Earth system. The chemical cycles, biological processes, and environmental conditions that we observe today all trace their origins back to the changes that occurred during this critical period in Earth's history. The Great Oxidation Event also provides important insights into the nature of global environmental change. The transformation of Earth's atmosphere occurred over timescales that are almost incomprehensible from a human perspective. Yet the changes were so fundamental that they affected every living organism on the planet. The event demonstrates how relatively small changes in biological activity can trigger cascading effects that reshape entire planetary systems. The gradual nature of the Great Oxidation Event also highlights the importance of threshold effects in environmental systems. For millions of years, oxygen production by cyanobacteria had little effect on atmospheric composition because the oxygen was immediately consumed by chemical reactions with reduced compounds in the environment. However, once these chemical buffers were exhausted, oxygen began to accumulate rapidly in the atmosphere, triggering the dramatic changes that followed. This threshold behavior is characteristic of many environmental systems and provides important lessons for understanding how planetary environments respond to perturbations. Small changes can accumulate over long periods without apparent effect until a critical threshold is crossed, at which point rapid and potentially irreversible changes can occur. The Great Oxidation Event provides a dramatic example of how these threshold effects can reshape entire planetary systems. The study of the Great Oxidation Event also demonstrates the power of geological and geochemical methods for reconstructing Earth's environmental history. The evidence for this ancient transformation is preserved in rocks that are billions of years old, recorded in subtle changes in isotopic composition, mineral assemblages, and sedimentary structures. These geological archives provide detailed records of environmental conditions that existed long before any human observers were present to witness them. The techniques used to study the Great Oxidation Event have been developed and refined over many decades of research, involving contributions from geologists, geochemists, biologists, and atmospheric scientists. The integration of evidence from multiple disciplines has been essential for developing a comprehensive understanding of this complex transformation. No single line of evidence would have been sufficient to reconstruct the full scope and significance of the Great Oxidation Event. The banded iron formations that provide some of the most compelling evidence for the Great Oxidation Event represent a unique type of geological archive that has no modern equivalent. These distinctive rock formations, with their alternating layers of iron-rich and iron-poor sediments, preserve a detailed record of the chemical changes that occurred in ancient oceans as oxygen levels rose. The careful study of these formations has provided crucial insights into the timing, pace, and geographic extent of oceanic oxygenation. The isotopic signatures preserved in ancient rocks provide another powerful tool for reconstructing the environmental conditions that existed during the Great Oxidation Event. The ratios of different isotopes of elements like sulfur, carbon, and molybdenum are sensitive indicators of the oxidation state of ancient environments. Changes in these isotopic ratios recorded in sedimentary rocks provide independent lines of evidence for the timing and magnitude of atmospheric and oceanic oxygenation. The integration of these diverse types of geological evidence has allowed scientists to reconstruct a detailed timeline of the Great Oxidation Event that extends over hundreds of millions of years. This timeline reveals the complex, non-linear nature of the transformation, with periods of rapid change alternating with intervals of relative stability. The detailed chronology made possible by geological studies has been essential for understanding the causes and consequences of this ancient environmental transformation. As we near the end of our journey through this transformative period in Earth's history, we must pause to consider the profound implications of what we have witnessed. The Great Oxidation Event represents one of the most dramatic examples of how life can reshape its own environment, triggering changes that affect the entire planetary system. The innovations of microscopic organisms led to transformations that altered atmospheric composition, ocean chemistry, climate, and the subsequent evolution of life itself. The story of the Great Oxidation Event is ultimately a story about the power of innovation and adaptation in the face of environmental change. The cyanobacteria that initiated this transformation were themselves responding to environmental pressures and opportunities, developing new metabolic capabilities that allowed them to exploit previously unavailable resources. Their success in developing oxygenic photosynthesis gave them access to the virtually unlimited energy source represented by sunlight and water. However, the success of cyanobacteria came at a tremendous cost to the rest of the biosphere. The oxygen they produced as a waste product was highly toxic to the anaerobic organisms that had dominated Earth's ecosystems for over 1 billion years. The rise of oxygen triggered one of the most severe extinction events in Earth's history, eliminating the vast majority of existing life forms and forcing the survivors to retreat to increasingly marginal environments. Yet this destruction also created new opportunities for evolutionary innovation. The organisms that survived the Great Oxidation Event were forced to develop new metabolic capabilities and cellular structures that could function in an oxygen-rich environment. The availability of oxygen opened up new metabolic pathways that were far more efficient than anything that had been possible under anaerobic conditions. The evolution of aerobic respiration provided organisms with access to energy budgets that were 20 times larger than those available through anaerobic metabolism. This dramatic increase in available energy created the foundation for evolutionary innovations that would have been impossible in the anaerobic world. Larger cell sizes, more complex cellular structures, and active lifestyles all became feasible once organisms gained access to the high energy yields of aerobic metabolism. The biochemical machinery necessary for complex multicellular life could only function with the abundant energy provided by oxygen-based metabolism. The organisms that successfully made the transition to aerobic metabolism found themselves in a world of unprecedented opportunity. The chemical energy stored in organic compounds, which had been largely inaccessible to anaerobic organisms, could now be extracted with remarkable efficiency. This energy revolution fundamentally altered the rules of biological existence, making possible forms of life that would have been energetically impossible in the pre-oxygen world. The development of oxygen-tolerant and oxygen-utilizing organisms was not a rapid process, but rather an evolutionary journey that unfolded over tens of millions of years. The first organisms to develop aerobic capabilities were likely bacteria that had evolved sophisticated enzyme systems capable of safely handling the reactive oxygen molecule. These pioneering aerobic bacteria had to solve multiple biochemical challenges simultaneously. The primary challenge was developing cellular machinery that could use oxygen for energy production without being destroyed by its toxic effects. Oxygen is an extremely reactive molecule that can damage virtually every type of biological molecule, from proteins and lipids to nucleic acids. Early aerobic organisms had to evolve complex antioxidant systems, repair mechanisms, and protective enzymes that could neutralize the harmful byproducts of oxygen metabolism. The evolution of these protective systems required fundamental changes in cellular biochemistry. New enzymes had to be developed that could safely transport oxygen within cells, control its reactions with other molecules, and repair the damage caused by a reactive oxygen species. The genetic machinery necessary to produce these enzymes had to evolve gradually, through countless generations of natural selection, favoring organisms with incrementally better oxygen tolerance. Simultaneously, these early aerobic organisms had to develop the metabolic pathways necessary to extract energy from oxygen reactions. The biochemical machinery of aerobic respiration is remarkably complex, involving dozens of enzymes and cofactors that must work together in precisely coordinated sequence. The evolution of this metabolic system represents one of the most sophisticated biochemical achievements in the history of life. The electron transport chain, the molecular assembly line that powers aerobic respiration, had to be constructed piece by piece through evolutionary processes. Each component of this system, from the initial electron donors to the final oxygen-reducing enzymes, required specific genetic innovations that had to be integrated into a functioning whole. The remarkable precision with which these components work together suggests that their evolution was a gradual process of refinement and optimization over millions of years. As these biochemical innovations accumulated in different lineages of bacteria, they created new ecological opportunities that had not existed in the anaerobic world. Aerobic bacteria could extract far more energy from the same organic resources, allowing them to grow faster, reproduce more frequently, and support larger population sizes than their anaerobic competitors. This energetic advantage gradually shifted the balance of power in microbial ecosystems toward oxygen-utilizing organisms. The success of aerobic bacteria also had important consequences for the continued evolution of atmospheric oxygen levels. As these organisms became more abundant and efficient, they increased the rate at which organic matter was decomposed and recycled in the environment. This accelerated recycling of organic compounds helped maintain the oxygen levels that had been established during the initial phases of the Great Oxidation Event. The relationship between aerobic organisms and atmospheric oxygen created a complex feedback system that helped stabilize oxygen concentrations at levels that could support continued aerobic life. When oxygen levels were high, aerobic decomposition proceeded rapidly, consuming organic matter and releasing carbon dioxide that could be used by photosynthetic organisms. When oxygen levels were low, organic matter accumulated in sediments, reducing the consumption of oxygen and allowing levels to recover. This feedback system represented a fundamental shift in the way that Earth's atmospheric composition was regulated. During the anaerobic era, atmospheric chemistry had been controlled primarily by physical and chemical processes, with biological activity playing a relatively minor role. After the Great Oxidation Event, biological processes became the dominant factor regulating atmospheric composition, creating a biologically mediated atmosphere that could respond dynamically to changes in environmental conditions. The emergence of this biologically regulated atmosphere had profound implications for the long-term stability of Earth's environment. The feedback mechanisms involving photosynthesis, respiration, and organic matter burial created a system that could maintain relatively stable oxygen levels, even in the face of perturbations from volcanic activity, asteroid impacts, or other environmental disturbances. This stability would prove crucial for the subsequent evolution of complex life forms that required consistent environmental conditions. The development of aerobic metabolism also enabled the evolution of new types of biological partnerships that would become increasingly important in later Earth history. Some organisms developed the ability to form symbiotic relationships with aerobic bacteria, gaining access to the energy-producing capabilities of aerobic metabolism without having to evolve the complete biochemical machinery themselves. These early symbiotic relationships would eventually lead to the evolution of eukaryotic cells, the complex cells that form the basis of all multicellular life. The integration of aerobic bacteria into larger cells through endosymbiosis represented another major evolutionary innovation that was made possible by the oxygen-rich environment created during the Great Oxidation Event. The bacteria that became incorporated into eukaryotic cells as mitochondria retained their aerobic metabolic capabilities while losing their independence, creating a permanent partnership that gave eukaryotic cells access to the high energy yields of aerobic respiration. This evolutionary innovation would prove to be one of the most significant developments in the history of life, as it provided the energetic foundation for all complex multicellular organisms. The evolution of plants, animals, fungi, and other complex life forms would not have been possible without the energy-producing capabilities of mitochondria, which trace their origin back to the free-living aerobic bacteria that evolved during the Great Oxidation Event. As the post-oxidation biosphere continued to evolve and diversify, the chemical cycles that regulate Earth's environment became increasingly complex and interconnected. The carbon cycle, which had been relatively simple during the anaerobic era, developed multiple pathways involving photosynthesis, respiration, decomposition, and mineral formation. The nitrogen cycle became more elaborate as organisms evolved new ways to fix atmospheric nitrogen and convert it into biologically useful compounds. The sulfur cycle also underwent fundamental changes as aerobic and anaerobic processes became spatially separated in different parts of the environment. In oxygen-rich surface waters, sulfur compounds were rapidly oxidized to sulfate, while in oxygen-poor deep waters and sediments, sulfur reduction continued to operate as it had during the anaerobic era. This spatial separation created redox gradients that influenced the distribution of organisms and the cycling of other essential elements. The phosphorus cycle, which had been relatively straightforward during the anaerobic era, became more complex as new mineral phases formed under oxidizing conditions. The availability of phosphorus, an essential nutrient for all life, became increasingly dependent on the chemical weathering of rocks and the recycling of organic matter by aerobic decomposers. These changes in phosphorus cycling would have long-term effects on the productivity and evolution of marine ecosystems. The trace element cycles that are essential for many biological processes also underwent significant changes during the post-oxidation period. Elements like iron, manganese, and molybdenum became less available to organisms as they formed insoluble compounds under oxidizing conditions. This reduced availability of trace elements created new types of nutrient limitation that influenced the evolution and distribution of different groups of organisms. The establishment of these complex biogeochemical cycles created a highly interconnected Earth system where changes in one component could have cascading effects throughout the entire system. The regulation of atmospheric oxygen levels became dependent on the balance between photosynthetic oxygen production, respiratory oxygen consumption, and the burial of organic matter in sediments. Small changes in any of these processes could potentially trigger significant shifts in atmospheric composition. This interconnectedness also meant that the Earth system developed a kind of environmental memory, where past events continued to influence present conditions long after they had occurred. The massive iron deposits formed during the Great Oxidation Event continued to affect ocean chemistry for hundreds of millions of years. The carbon compounds buried in sediments during periods of high productivity could be released back into the atmosphere during later periods of tectonic activity. The development of this complex, interconnected Earth system represented the maturation of the planet's environmental regulatory mechanisms. The simple, chemically controlled atmosphere of the early Earth had been replaced by a sophisticated system where biological, chemical, and physical processes worked together to maintain conditions suitable for life. This system would continue to evolve and become more complex over the billions of years that followed. As we trace the environmental changes that occurred during the later phases of the Great Oxidation Event, we can observe the gradual emergence of many features that characterize the modern Earth system. The stratified ocean chemistry that developed during this period, with oxygen-rich surface waters overlying oxygen-poor deep waters, established patterns that persist to this day. The seasonal and geographic variations in oxygen levels that resulted from the interplay between photosynthesis and respiration created temporal and spatial complexity that would influence the evolution of all subsequent life. The climate system that emerged from the post-oxidation period was also fundamentally different from what had existed during the anaerobic era. The presence of oxygen and ozone in the atmosphere created new pathways for atmospheric chemistry and energy transfer. The weathering processes initiated by oxygen-rich air and water established new mechanisms for removing carbon dioxide from the atmosphere, creating feedbacks that would influence global climate over geological timescales. The formation of soils under oxidizing conditions created new habitats that would eventually be colonized by living organisms. The chemical weathering of rocks in the presence of oxygen and water produced mineral assemblages that were rich in nutrients and capable of supporting plant growth. These early soils represented the first step toward the terrestrial ecosystems that would develop hundreds of millions of years later. The establishment of stable oxygen levels in the atmosphere also created conditions that could support the formation of more complex organic molecules. Many of the biochemical compounds that are essential for advanced cellular functions, including sterols and other membrane lipids, require oxygen for their synthesis. The availability of oxygen thus opened up new possibilities for cellular complexity and sophistication that had been impossible under anaerobic conditions. The gradual increase in atmospheric oxygen levels during the post-snowball Earth period also had important effects on the evolution of photosynthetic organisms themselves. Higher oxygen concentrations created challenges for photosynthesis, as oxygen can interfere with the carbon-fixing enzymes used by plants and other photosynthetic organisms. This led to the evolution of new types of photosynthetic machinery that were more efficient under high oxygen conditions. The development of these improved photosynthetic systems allowed primary productivity to increase even as oxygen levels continued to rise. This increased productivity supported more complex food webs and higher levels of biological activity than had been possible during the early stages of the Great Oxidation event. The combination of efficient photosynthesis and aerobic respiration created the energetic foundation for the complex ecosystems that would characterize later Earth history. As atmospheric oxygen levels stabilized at concentrations that could support aerobic life, the pace of evolutionary innovation began to accelerate. The energy abundance made possible by aerobic metabolism allowed organisms to experiment with new body plans, life strategies, and ecological relationships. The diversification of life that occurred during this period laid the groundwork for all subsequent biological evolution. The development of more sophisticated cellular structures was one of the most important evolutionary innovations of this period. The abundant energy provided by aerobic metabolism made it possible to maintain complex internal cellular organization, including membrane-bound organelles and elaborate cytoskeletal systems. These structural innovations were essential prerequisites for the evolution of multicellular organisms. The evolution of multicellularity itself was made possible by the stable, oxygen-rich environment that had been established by the Great Oxidation event. The coordination of activities between multiple cells required sophisticated signaling systems and energy-intensive communication mechanisms that could only function with the high energy yields of aerobic metabolism. The transition from single-celled to multicellular life represented another fundamental threshold in biological evolution. The first multicellular organisms were simple assemblages of similar cells that worked together to perform basic functions like locomotion and feeding. However, the availability of abundant energy from aerobic metabolism allowed these early multicellular organisms to develop specialized cell types that could perform different functions more efficiently than generalized cells. This cellular specialization was the beginning of the complex tissue and organ systems that characterize advanced multicellular life. The evolution of specialized tissues created new possibilities for organism design and function. Cells could be optimized for specific tasks like photosynthesis, locomotion, or reproduction, allowing multicellular organisms to achieve levels of performance that were impossible for single-celled organisms. The energy requirements of these specialized tissues could be met by the efficient energy production systems that had evolved in response to the oxygen-rich environment. As multicellular organisms became more complex and sophisticated, they began to have increasingly significant effects on their environment. Large photosynthetic organisms could modify local light conditions, nutrient availability, and water chemistry. Mobile organisms could transport nutrients and energy across different habitats, creating new patterns of resource distribution. These biological modifications of the environment created additional complexity in the Earth system. The emergence of complex multicellular life also marked the beginning of more sophisticated ecological relationships. Predation, parasitism, and other forms of biological interaction became possible as organisms developed the energy budgets and structural complexity necessary to support active lifestyles. These ecological relationships created new selective pressures that drove further evolutionary innovation and diversification. The development of hard shells, skeletons, and other structural elements by some multicellular organisms was made possible by the chemical conditions that had been established during the Great Oxidation Event. The precipitation of calcium carbonate and other minerals required specific chemical conditions that were only available in the oxygen-rich, chemically complex environment that had emerged from the atmospheric transformation. These structural innovations had important consequences for the preservation of organisms in the fossil record. The hard parts that evolved during this period were much more likely to be preserved as fossils than the soft tissues of earlier organisms, creating a dramatic improvement in the quality and quantity of paleontological evidence available to scientists studying this period of Earth history. The fossil record that accumulated during the post-oxidation period provides detailed evidence for the rapid diversification of life that occurred once stable oxygen levels had been established. This diversification event, which occurred approximately 1 billion years ago, marked the beginning of the evolutionary radiation that would eventually lead to all modern groups of complex organisms. The timing of this diversification event was not coincidental, but rather represented the biological response to the environmental opportunities created by the Great Oxidation Event. The stable, oxygen-rich environment provided the energy and chemical conditions necessary to support complex multicellular life, while the diverse chemical gradients and habitat types that had emerged during the atmospheric transformation provided numerous ecological niches for evolutionary exploration. As we observe the biological innovations that emerged during this period, we can see how each evolutionary advance built upon the environmental foundations established by the Great Oxidation Event. The oxygen that had initially been a toxic waste product became the essential fuel for high-energy metabolism. The chemical complexity that had resulted from atmospheric oxidation provided the materials necessary for sophisticated biochemical systems. The climate stability that had been established by the feedback mechanisms involving oxygen, carbon dioxide, and biological activity created predictable environmental conditions that could support long-term evolutionary projects like the development of complex multicellular body plans. The protection from ultraviolet radiation provided by the ozone layer made it safe for organisms to explore new habitats and develop new structural materials. The legacy of the Great Oxidation Event thus extended far beyond the immediate environmental changes that occurred during the atmospheric transformation itself. The event established the chemical, energetic, and environmental conditions that made possible all subsequent biological evolution, from the first simple multicellular organisms to the complex ecosystems that characterize the modern world. As we reflect on this vast transformation through deep time, we must appreciate the profound ways in which the Great Oxidation Event reshaped not just the chemistry of Earth's atmosphere and oceans, but the very nature of life itself. The anaerobic world that had existed for the first 2 billion years of Earth history was characterized by simple, single-celled organisms that extracted modest amounts of energy from chemical reactions that did not require oxygen. The post-oxidation world that emerged from this transformation was fundamentally different, characterized by complex ecosystems powered by efficient energy production systems and regulated by sophisticated biogeochemical cycles. The transition between these two states represents one of the most dramatic system-level changes in Earth's history, comparable in scope to the formation of the oceans or the solidification of the planet's crust. The Great Oxidation Event demonstrates the capacity of biological innovation to trigger planetary-scale environmental changes. The evolution of oxygenic photosynthesis by cyanobacteria was initially just another metabolic innovation in the long history of bacterial evolution. However, the particular characteristics of this innovation, its ability to use water as an electron donor, and its production of oxygen as a waste product, gave it the potential to transform the entire planetary system. This transformation occurred not through the conscious intention of the organisms involved, but rather through the accumulation of countless individual biological activities over vast spans of geological time. Each cyanobacterial cell that split a water molecule and released oxygen into its environment was simply following its genetic programming, seeking energy and resources for growth and reproduction. The collective effect of billions of these individual actions was to fundamentally alter the chemical composition of Earth's atmosphere. The unintended consequences of biological innovation, demonstrated during the Great Oxidation Event, provide important insights into the nature of planetary-scale environmental change. Small changes in biological activity can accumulate over long periods to produce effects that are far larger than the original innovations that triggered them. The feedback mechanisms that operate within Earth's environmental systems can amplify these effects, creating cascading changes that affect every component of the planetary system. The Great Oxidation Event also illustrates the importance of threshold effects in environmental systems. For millions of years, the oxygen produced by cyanobacteria was immediately consumed by chemical reactions with reduced compounds in the environment, producing no apparent change in atmospheric composition. However, once the capacity of these chemical sinks was exhausted, oxygen began to accumulate rapidly in the atmosphere, triggering the dramatic changes that followed. This threshold behavior is characteristic of many complex systems and helps explain why environmental changes often appear to occur suddenly, even when they result from gradual, underlying processes. The apparent suddenness of environmental transitions can mask the long periods of gradual change that preceded them, making it difficult to predict when critical thresholds will be crossed. The study of the Great Oxidation Event has required the development and application of sophisticated analytical techniques that can extract environmental information from rocks that are billions of years old. The isotopic signatures, mineral assemblages, and trace element patterns preserved in ancient rocks provide the only direct evidence for the environmental conditions that existed during this critical period in Earth history. The interpretation of this geological evidence requires careful consideration of the processes that could have produced the observed chemical signatures. Scientists must distinguish between signatures that reflect ancient environmental conditions and those that result from later alteration of the rocks. This analytical challenge has driven the development of increasingly sophisticated geochemical techniques and theoretical frameworks for understanding ancient environmental systems. The integration of evidence from multiple geological and geochemical indicators has been essential for developing a comprehensive understanding of the Great Oxidation Event. No single type of evidence would have been sufficient to reconstruct the full scope and complexity of this ancient environmental transformation. The convergence of evidence from different analytical approaches provides confidence in the scientific understanding of this critical period in Earth history. The interdisciplinary nature of research on the Great Oxidation Event reflects the inherently interdisciplinary character of Earth systems science. Understanding this ancient environmental transformation requires expertise in geology, geochemistry, biology, atmospheric science, oceanography, and other fields. The integration of knowledge from these diverse disciplines has been essential for developing a complete picture of how the event unfolded and what its consequences were. The collaborative nature of research on the Great Oxidation Event also demonstrates the cumulative character of scientific understanding. The current knowledge of this event has been built up over many decades through the contributions of hundreds of scientists working at institutions around the world. Each new study has added pieces to the puzzle, gradually revealing the complete picture of this ancient transformation. The ongoing research on the Great Oxidation Event continues to refine and expand our understanding of this critical period in Earth history. New analytical techniques are providing increasingly detailed information about the timing, pace, and geographic extent of atmospheric and oceanic changes. Advanced computer models are helping scientists understand the complex interactions between biological, chemical, and physical processes that drove the transformation. As our understanding of the Great Oxidation Event continues to evolve, it provides increasingly sophisticated insights into the nature of planetary-scale environmental change. The event serves as a natural laboratory for studying how complex Earth systems respond to major perturbations. The lessons learned from studying this ancient transformation are relevant for understanding how Earth's environment might respond to future changes. The Great Oxidation Event also provides important perspectives on the relationship between life and environment. The event demonstrates that life is not simply a passive responder to environmental conditions, but rather an active agent that can reshape its own environment in fundamental ways. The capacity of life to modify planetary-scale environmental conditions has been a major factor in Earth's environmental evolution throughout geological history. The co-evolution of life and environment that is exemplified by the Great Oxidation Event continues to operate today. Modern biological activities continue to influence atmospheric composition, ocean chemistry, and climate, just as they did during the ancient atmospheric transformation. Understanding these ongoing interactions is essential for predicting how Earth's environment will evolve in the future. As we bring our journey through this ancient transformation toward its conclusion, we must pause to consider the profound legacy that the Great Oxidation Event has left for the modern world. The oxygen that we breathe with every breath, the ozone layer that protects us from harmful radiation, and the complex ecosystems that surround us all trace their origins back to the changes that occurred during this critical period in Earth history. The energy that powers our bodies through aerobic respiration was made available by the evolutionary innovations that emerged in response to rising oxygen levels. The complex multicellular organisms that form the basis of all terrestrial and marine ecosystems could not exist without the energetic foundation provided by oxygen-based metabolism. The very possibility of complex life as we know it was created by the environmental transformation that occurred during the Great Oxidation Event. The chemical cycles that regulate Earth's climate and maintain environmental conditions suitable for life were established during the post-oxidation period. The feedback mechanisms involving photosynthesis, respiration, and organic matter burial continue to operate today, maintaining the atmospheric composition that supports the complex biosphere we observe in the modern world. The geological record that preserves evidence of the Great Oxidation Event also provides crucial insights into the long-term behavior of Earth's environmental systems. The patterns of environmental change recorded in ancient rocks help scientists understand the natural variability of Earth's climate and atmospheric composition over geological timescales. This understanding provides important context for assessing modern environmental changes. The study of the Great Oxidation Event has also contributed to our understanding of how life might evolve on other planets. the specific sequence of environmental and biological changes that occurred during Earth's atmospheric transformation provides a template for understanding how planetary environments might evolve elsewhere in the universe. The event demonstrates that the evolution of complex life requires not just suitable initial conditions, but also major environmental transformations that create new ecological opportunities. As we contemplate the vast scope of this ancient transformation, we are reminded of the deep interconnectedness of all Earth's environmental systems. The Great Oxidation Event was not an isolated biological or chemical phenomenon, but rather a system-level transformation that involved complex interactions between atmosphere, oceans, life, and the solid Earth. Understanding these interactions is essential for comprehending how Earth's environment has evolved and how it might change in the future. The timescales over which the Great Oxidation Event unfolded also provide important perspectives on the pace of planetary-scale environmental change. The transformation occurred over hundreds of millions of years, a duration that encompasses thousands of times the entire span of human civilization. This deep time perspective helps us appreciate both the stability and the capacity for change that characterize Earth's environmental systems. The gradual nature of the Great Oxidation Event demonstrates that even the most dramatic planetary transformations typically unfold over geological timescales that are vast compared to human experience. However, the event also shows that these gradual changes can cross critical thresholds that trigger rapid and dramatic shifts in environmental conditions. Understanding both the gradual and rapid components of environmental change is essential for predicting how Earth's systems might respond to future perturbations. The Great Oxidation Event ultimately represents a story of transformation, adaptation, and renewal that played out over unimaginable spans of time. It tells us that Earth's environment is not static, but rather dynamic, capable of fundamental changes that can reshape the conditions for life. It shows us that biological innovation can have consequences that extend far beyond the organisms that create the innovations, affecting the entire planetary system for billions of years. As we drift back through these vast reaches of time toward our present moment, we carry with us an appreciation for the profound changes that have shaped our world. The air we breathe, the water we drink, and the land we walk upon all bear the chemical signatures of this ancient transformation. Every breath we take connects us to the cyanobacteria that first learned to split water molecules and release oxygen into the ancient seas. The Great Oxidation Event reminds us that we are part of a planetary story that extends far beyond human history, a story of environmental change and biological innovation that has been unfolding for billions of years. Understanding this deep history helps us appreciate our place in the larger narrative of Earth's evolution and the profound interconnections that link all life to the planetary environment that sustains it. In the end, the story of Earth's atmospheric transformation during the Great Oxidation Event is also our story. The environmental conditions that make human civilization possible were created by the changes that occurred during this ancient period. The oxygen that powers our metabolism, the ozone that protects us from radiation, and the stable climate that supports our agriculture all trace their origins to this pivotal moment in planetary history. As we rest in the knowledge of these deep connections, we can appreciate the remarkable journey that our planet has taken from its early anaerobic state to the oxygen-rich world we inhabit today. The Great Oxidation Event stands as testament to the power of life to reshape its environment and to the capacity of planetary systems to undergo fundamental transformations while still maintaining the conditions necessary for life to persist and flourish. The ancient transformation that turned Earth's air from poison to life-giving breath continues to shape our world today, reminding us of the profound and enduring connections between all life and the planetary environment that we share. In understanding this ancient story, we gain deeper appreciation for the remarkable world we inhabit and our place within the vast tapestry of Earth's environmental history. The organisms that survived this great transition found themselves living in a fundamentally different world, one where the very rules of existence had been rewritten by the accumulation of a single reactive molecule. As oxygen levels gradually stabilized in the post-glaciation atmosphere, reaching concentrations that could sustain the complex chemistry of aerobic life, the survivors began to explore the new possibilities that this transformed environment offered. The marine ecosystems that emerged from the snowball Earth period were unlike anything that had existed in the previous 2 billion years of Earth's history. Where once the oceans had been chemically uniform from surface to depth, now they displayed a complex three-dimensional structure of chemical gradients that created distinct zones of biological opportunity. Near the surface, where sunlight could penetrate and photosynthesis flourished, oxygen concentrations approached levels that could support active, energy-intensive lifestyles. In these oxygen-rich surface waters, a new type of biological community began to take shape. The cyanobacteria that had triggered the Great Transformation continued to thrive, their populations expanding and diversifying as they adapted to the high-oxygen environment they had created. But they were no longer alone in their photosynthetic endeavors. Other groups of organisms began to evolve similar capabilities, developing their own versions of the molecular machinery necessary to capture sunlight and convert it into usable energy. These early photosynthetic communities created vast underwater meadows that stretched across the continental shelves, their growth patterns following the rhythms of sunlight and season that had become the new organizing principles of marine life. The oxygen they produced during daylight hours accumulated in the surrounding water, creating microenvironments where oxygen concentrations could fluctuate dramatically over the course of a single day. Below these productive surface waters lay a vast intermediate zone where oxygen levels were lower but still detectable. Here, in the twilight realm between the oxygen-rich surface and the oxygen-poor depths, a remarkable group of organisms began to evolve the ability to live in both worlds. These metabolically flexible bacteria could switch between aerobic and anaerobic pathways depending on the local availability of oxygen, positioning themselves at the intersection of the old world and the new. The evolution of this metabolic flexibility represented a crucial adaptation to the chemically stratified oceans of the post-oxidation world. Organisms that could function under variable oxygen conditions were able to exploit resources that were unavailable to those locked into a single metabolic strategy. They could migrate vertically through the water column, following optimal chemical conditions as they changed with depth and time. In the deepest parts of the oceans, where sunlight never penetrated and oxygen remained scarce, the survivors of the ancient anaerobic world continued to carry out the metabolic processes that had sustained life for billions of years. These deep water communities became living museums of Earth's pre-oxygen past, preserving biochemical pathways and ecological relationships that had once dominated the entire planet. The chemical boundary between the oxygen-rich surface waters and the oxygen-poor deep waters was not a sharp line, but rather a gradient zone where conditions changed gradually with depth. This transition zone, known as the chemocline, became one of the most biologically active regions of the post-oxidation oceans. Here, organisms from both the aerobic and anaerobic worlds could coexist, creating complex ecological interactions that had been impossible in the chemically uniform oceans of the past. The establishment of these vertical chemical gradients in the oceans had profound effects on the cycling of nutrients and other essential elements. In the oxygen-rich surface waters, the rapid decomposition of organic matter by aerobic bacteria ensured that nutrients were quickly recycled and made available for new photosynthetic production. This efficient recycling created a positive feedback loop that supported high levels of biological productivity in the surface ocean. However, the same oxygen that enabled efficient nutrient recycling in surface waters also created challenges for the transport of nutrients from deeper parts of the ocean. Many essential nutrients, particularly iron, became much less soluble under oxidizing conditions, forming insoluble compounds that settled out of the water column before they could reach the surface where photosynthetic organisms needed them. This nutrient limitation began to shape the evolution and distribution of marine life in ways that had never been important during the anaerobic era. Organisms that could access or efficiently utilize scarce nutrients gained significant competitive advantages, driving the evolution of increasingly sophisticated strategies for nutrient acquisition and conservation. Some organisms evolved specialized structures for capturing and concentrating nutrients from the surrounding water. Others developed symbiotic relationships with bacteria that could convert atmospheric nitrogen into biologically useful compounds, providing access to this essential nutrient even when dissolved forms were scarce. Still others evolved the ability to migrate vertically through the water column, traveling to nutrient-rich deep waters to feed and then returning to the sunlit surface to photosynthesize. These evolutionary innovations created new types of ecological relationships that added complexity to the simple food webs that had characterized the anaerobic world. The evolution of predation, where one organism actively hunted and consumed another, became possible as organisms developed the energy budgets and sensory capabilities necessary to support active lifestyles. The abundant energy provided by aerobic metabolism made it possible for some organisms to invest in sophisticated sensory systems that could detect prey, predators, or favorable environmental conditions. The evolution of light-sensing organs, chemical receptors, and mechanical sensors opened up new ways of interacting with the environment that had been energetically impossible under anaerobic conditions. The development of active locomotion was another major evolutionary innovation that became feasible in the high-energy world of aerobic metabolism. The ability to swim actively through the water column, rather than simply drifting with the currents, allowed organisms to seek out favorable conditions and avoid unfavorable ones. This mobility fundamentally changed the nature of ecological interactions, creating new possibilities for both cooperation and competition. As these innovations accumulated in different lineages of organisms, the marine ecosystems of the post-oxidation world began to display levels of complexity and dynamism that had been unimaginable during the anaerobic era. The simple microbial mats that had dominated the ancient seafloor gave way to complex three-dimensional communities, where organisms occupied distinct ecological niches and interacted through elaborate networks of predation, competition, and cooperation. The fossil record from this period preserves evidence of these increasingly complex biological communities. The stromatolites formed by cyanobacterial mats began to show more sophisticated internal structures that reflect the complex chemical gradients and biological interactions occurring within these microbial communities. The diversity of fossil forms preserved from this period is dramatically higher than what is found in rocks from the anaerobic era, indicating a rapid expansion in the variety of life forms that the oxygenated environment could support. The chemical signatures preserved in these ancient rocks also record the establishment of biogeochemical cycles that were far more complex than anything that had existed during the anaerobic period. The carbon cycle, in particular, developed multiple interconnected pathways that linked atmospheric carbon dioxide, dissolved carbon in seawater, organic carbon in living organisms, and carbonate minerals in marine sediments. The complexity of these biogeochemical cycles created new forms of environmental regulation that helped stabilize conditions in the post-oxidation world. When photosynthetic production was high, large amounts of carbon dioxide were removed from the atmosphere and converted into organic matter, reducing the greenhouse effect and cooling the planet. When photosynthetic production was low, less carbon dioxide was removed, allowing temperatures to rise and potentially stimulating increased biological activity. These feedback mechanisms created a form of planetary scale homeostasis that helped maintain environmental conditions within ranges that could support continued biological activity. The evolution of these regulatory mechanisms marked the transition from a purely physical and chemical Earth system to a biologically mediated system where life played an active role in controlling environmental conditions. The establishment of this biologically regulated Earth system was not a smooth or simple process. The complex interactions between biological, chemical, and physical processes created a system that was capable of multiple stable states, each characterized by different atmospheric compositions, ocean chemistry, and biological communities. The transition between these states could be triggered by relatively small perturbations, leading to rapid and sometimes dramatic changes in environmental conditions. During the post-snowball Earth period, the Earth system experienced several of these transitions as it gradually settled into the stable configuration that would characterize the remainder of Earth's history. The most dramatic of these transitions occurred around 2 billion years ago, when oxygen levels temporarily rose to concentrations that may have exceeded modern atmospheric levels before declining to much lower values. This period of high oxygen concentrations, known as the Lomagundi event, lasted for more than 100 million years and had profound effects on both biological evolution and global biogeochemical cycles. The extremely high oxygen levels supported new types of biological activity while simultaneously creating challenges for organisms that were adapted to lower oxygen concentrations. The cause of the Lomagundi event is still not fully understood, but it appears to have been related to changes in the global carbon cycle that led to the massive burial of organic matter in marine sediments. This burial removed carbon from the ocean atmosphere system, while leaving behind the oxygen that had been produced during photosynthesis, causing atmospheric oxygen levels to rise to unprecedented heights. The end of the Lomagundi event was marked by a dramatic decline in oxygen levels that may have triggered another significant extinction event. This decline appears to have been caused by the oxidation of the massive organic carbon deposits that had accumulated during the high oxygen period, consuming atmospheric oxygen and returning carbon dioxide to the atmosphere. These dramatic fluctuations in atmospheric composition during the post-oxidation period demonstrate the dynamic nature of the Earth system during this critical phase in planetary evolution. The establishment of stable, life-supporting conditions required the evolution of robust regulatory mechanisms that could maintain environmental stability despite the complex interactions between biological and geochemical processes. The development of these regulatory mechanisms was facilitated by the evolution of increasingly sophisticated biological communities that could respond to environmental changes in ways that helped restore stability. When oxygen levels became too high, organisms that could tolerate high oxygen conditions flourished, increasing the consumption of oxygen through respiration and reducing oxygen levels. When oxygen levels became too low, photosynthetic organisms gained competitive advantages, increasing oxygen production and raising atmospheric levels. The evolution of these biological feedback mechanisms was crucial for the long-term stability of the oxygen-rich atmosphere that had been established during the Great Oxidation Event. Without these regulatory mechanisms, the Earth system might have continued to experience the dramatic oscillations in atmospheric composition that characterized the immediate post-oxidation period. As these regulatory mechanisms became more sophisticated and robust, the Earth system gradually settled into the stable configuration that has persisted for the past 2 billion years. Atmospheric oxygen levels stabilized at concentrations that could support aerobic metabolism while remaining low enough to prevent the spontaneous combustion of organic matter. The carbon cycle developed stable pathways for the exchange of carbon between atmosphere, oceans, and living organisms. The establishment of this stable Earth system marked the end of the Great Oxidation Event and the beginning of a new phase in planetary evolution. The chemical and biological foundations for complex life had been established, and the stage was set for the evolutionary innovations that would eventually lead to the emergence of multicellular organisms. The transition to multicellularity was made possible by the abundant energy and stable environmental conditions that had been established during the Great Oxidation Event. The complex cellular structures and sophisticated communication systems required for multicellular life could only function with the high energy yields provided by aerobic metabolism. The stable atmospheric and oceanic chemistry provided the predictable environmental conditions necessary for the long-term evolutionary projects that multicellular development represents. The first multicellular organisms were simple assemblages of similar cells that cooperated to perform basic functions like feeding and reproduction. These early multicellular forms were not dramatically different from the colonial bacteria that had existed during the anaerobic era, but they represented the first steps toward the complex multicellular body plans that would eventually characterize advanced life forms. The evolution of cellular specialization within multicellular organisms was driven by the energetic advantages of division of labor. When different cells within an organism could specialize for different functions, the overall efficiency of the organism could be greatly improved. Some cells could specialize for energy production, others for structural support, still others for reproduction or sensory functions. This cellular specialization was only possible because of the abundant energy provided by aerobic metabolism. The maintenance of specialized cell types required sophisticated regulatory mechanisms and communication systems that consumed significant amounts of energy. Under the energy-limited conditions of the anaerobic world, such specialization would have been prohibitively expensive. The development of specialized tissues and organ systems within multicellular organisms created new possibilities for organism design and function. Organisms could evolve complex body plans that were optimized for specific environments or lifestyles. The evolution of hard shells, internal skeletons, and other structural elements provided support for larger body sizes and more complex shapes. The availability of oxygen also enabled the evolution of active lifestyles that had been impossible under anaerobic conditions. The high energy yields of aerobic metabolism could support the metabolic demands of active locomotion, allowing organisms to swim, crawl, or burrow through their environments. This mobility opened up new ecological niches and created new opportunities for both predation and escape from predators. The evolution of sophisticated sensory systems was another major innovation that was made possible by the energy abundance of the post-oxidation world. The development of eyes, ears, chemical sensors, and other sensory organs required significant energy investments, but provided organisms with detailed information about their environments that could be used to locate food, avoid predators, and find mates. The combination of active locomotion and sophisticated sensory systems created the foundation for complex behavioral repertoires that added new dimensions to ecological interactions. Organisms could now engage in elaborate courtship displays, territorial behaviors, and cooperative activities that had been impossible in the simpler world of anaerobic microbes. These behavioral innovations, in turn, drove the evolution of increasingly complex nervous systems that could process sensory information and coordinate behavioral responses. The evolution of centralized nervous systems and eventually primitive brains represented another major advance that was made possible by the energetic foundation established during the Great Oxidation Event. As multicellular organisms became larger and more complex, they began to have increasingly significant effects on their environments. Large photosynthetic organisms could modify local light conditions and nutrient availability. Active predators could influence the behavior and distribution of their prey. Burrowing organisms could alter sediment structure and chemistry. These biological modifications of the environment created additional complexity in ecological systems and drove further evolutionary innovation. Organisms that could take advantage of environmentally modified habitats gained competitive advantages, while those that were negatively affected faced new selective pressures that drove adaptive responses. The increasing complexity of biological communities during the post-oxidation period also led to the evolution of more sophisticated ecological relationships. Symbiotic partnerships between different organisms became increasingly common as the benefits of cooperation became apparent. Some organisms evolved to live inside others, providing specialized services in exchange for protection or resources. The evolution of these symbiotic relationships was particularly important for the development of eukaryotic cells, the complex cells that form the basis of all multicellular life. The incorporation of aerobic bacteria into larger cells as mitochondria provided eukaryotic cells with access to the high energy yields of aerobic metabolism, while allowing the bacterial partners to specialize for energy production. This endosymbiotic relationship was so successful that it became permanent, with the bacterial partners losing their ability to live independently while retaining their capacity for aerobic energy production. The mitochondria that power modern eukaryotic cells are the direct descendants of these ancient bacterial partners, preserving in their genetic material evidence of their origin as free-living aerobic bacteria. The evolution of eukaryotic cells marked another major milestone in the development of complex life. Eukaryotic cells are much larger and more structurally complex than bacterial cells, with elaborate internal organization that includes membrane-bound organelles and sophisticated regulatory systems. This cellular complexity was essential for the evolution of multicellular organisms with specialized tissues and organ systems. The larger size and internal complexity of eukaryotic cells also made possible new forms of genetic regulation that enabled more sophisticated responses to environmental changes. The evolution of sexual reproduction, which allows for the recombination of genetic material from different individuals, created new mechanisms for generating genetic diversity that accelerated the pace of evolutionary innovation. The combination of sexual reproduction, multicellularity, and aerobic metabolism created a powerful engine for evolutionary diversification that led to the rapid expansion of biological complexity during the later phases of Earth's history. The fossil record from this period documents an explosive increase in the diversity of life forms, with new body plans and ecological strategies appearing at an unprecedented rate. This diversification event, which occurred approximately 1 billion years ago, marked the beginning of the evolutionary radiation that would eventually lead to all modern groups of complex organisms. The timing of this radiation was directly linked to the environmental conditions that had been established during the Great Oxidation Event, demonstrating the fundamental importance of atmospheric oxygenation for the evolution of complex life. The plants, animals, and fungi that dominate modern ecosystems all trace their evolutionary origins to the innovations that emerged during this period of rapid diversification. The photosynthetic organisms that form the base of modern food webs, the mobile animals that occupy countless ecological niches, and the decomposer organisms that recycle nutrients, all evolved from the simple eukaryotic cells that first appeared in the post-oxidation oceans. The terrestrial ecosystems that characterize the modern world were also made possible by the environmental changes that occurred during the Great Oxidation Event. The formation of the ozone layer provided protection from ultraviolet radiation that made it safe for organisms to venture onto land. The oxygen-rich atmosphere provided the respiratory gas necessary to support active terrestrial lifestyles. The colonization of land by living organisms was a gradual process that began with simple photosynthetic organisms in shallow coastal waters and eventually led to the complex terrestrial ecosystems that cover the continents today. This colonization was only possible because of the chemical and energetic foundations that had been established during the atmospheric transformation of the Great Oxidation Event. The soils that support terrestrial plant life were formed through the chemical weathering of rocks under the oxidizing conditions that had been established during the atmospheric transformation. The complex mineral assemblages found in modern soils reflect the oxygen-rich chemical environment that has persisted for the past 2 billion years. The atmospheric composition that supports modern terrestrial life is also a direct legacy of the Great Oxidation Event. The oxygen that we breathe with every breath was first released into the atmosphere by the photosynthetic activities of ancient cyanobacteria. The carbon dioxide that plants use for photosynthesis is regulated by biogeochemical cycles that were established during the post-oxidation period. The climate system that maintains the temperature and precipitation patterns necessary for terrestrial life is also fundamentally dependent on the atmospheric composition that emerged from the Great Oxidation Event. The presence of oxygen and ozone in the atmosphere affects the absorption and scattering of solar radiation, while the biogeochemical cycles involving oxygen and carbon dioxide help regulate global temperatures over long timescales. As we trace the connections between the ancient atmospheric transformation and the modern world, we begin to appreciate the profound and lasting impact that the Great Oxidation Event has had on every aspect of life on Earth. The energy that powers our bodies, the air that we breathe, and the complex ecosystems that surround us all depend on the environmental conditions that were established during this critical period in planetary history. The chemical elements that make up our bodies were processed through the biogeochemical cycles that were established during the post-oxidation period. The carbon in our tissues was once carbon dioxide in the atmosphere, converted into organic matter by photosynthetic organisms using the energy of sunlight. The oxygen in our blood was released by plants during photosynthesis, continuing the ancient process that began with cyanobacteria billions of years ago. The complex molecular machinery that enables our cells to function efficiently is also a direct descendant of the biochemical innovations that emerged in response to the oxygen-rich environment created during the Great Oxidation Event. The mitochondria that power our cellular metabolism preserve in their structure and function the legacy of the ancient bacterial partnerships that first learned to use oxygen for energy production. The genetic information that guides our development and maintains our biological functions includes sequences that can be traced back to the organisms that survived the Great Atmospheric Transformation. The genes that encode the enzymes necessary for aerobic respiration, the proteins that protect our cells from oxidative damage, and the regulatory systems that control our responses to environmental changes all evolved during the post-oxidation period. Even our sensory experiences of the world around us are shaped by the environmental conditions that were established during the Great Oxidation Event. The colours that we see in the natural world reflect the wavelengths of light that can penetrate the ozone-protected atmosphere. The sounds that we hear are transmitted through air with the density and composition that emerge from the atmospheric transformation. The landscapes that surround us bear the chemical signatures of billions of years of interaction between the atmosphere, oceans, and living organisms under the oxidizing conditions that were established during the Great Oxidation Event. The red soils and rocks that characterize many terrestrial environments reflect the oxidation of iron-bearing minerals under oxygen-rich atmospheric conditions. The rivers and lakes that provide fresh water for terrestrial life maintain their chemical composition through interactions with the atmosphere and surrounding rocks that are fundamentally different from the processes that operated during the anaerobic era. The dissolved gases, nutrients, and minerals found in freshwater environments reflect the complex biogeochemical cycles that were established during the post-oxidation period. The oceans that cover most of Earth's surface continue to display the chemical stratification that was established during the Great Oxidation Event. The oxygen-rich surface waters that support marine photosynthesis and the oxygen-poor deep waters where ancient anaerobic processes continue to operate maintain the basic structure that emerged from the atmospheric transformation billions of years ago. The seasonal cycles that regulate biological activity in both terrestrial and marine environments are also linked to the atmospheric composition that emerged from the Great Oxidation Event. The production and consumption of oxygen by photosynthesis and respiration create daily and seasonal fluctuations in atmospheric composition that influence weather patterns, ocean circulation, and biological rhythms. The global cycles of carbon, nitrogen, sulfur, and other essential elements that maintain the chemical balance necessary for life continue to operate through the pathways that were established during the post-oxidation period. These cycles link the atmosphere oceans, land surface, and living organisms in a complex web of interactions that maintains environmental stability over geological timescales. The fossil fuels that powered the Industrial Revolution and continue to influence modern society are composed of organic matter that was formed under the oxidizing conditions established during the Great Oxidation Event. The coal, oil, and natural gas that we extract from ancient sedimentary rocks preserve the carbon that was once incorporated into living organisms billions of years ago. Even the challenges that modern society faces in managing environmental change can be understood in the context of the lessons learned from studying the Great Oxidation Event. The event demonstrates how biological innovations can trigger planetary-scale environmental changes that persist for billions of years. It shows how complex Earth systems can undergo rapid transitions between different stable states when critical thresholds are crossed. The study of the Great Oxidation Event has also contributed to our understanding of how life might evolve on other planets. The specific sequence of environmental and biological changes that occurred during Earth's atmospheric transformation provides a template for understanding how planetary environments might evolve elsewhere in the universe. The techniques that scientists have developed to study the Great Oxidation Event, including the analysis of ancient rocks and the reconstruction of past environmental conditions, are also being applied to study other planets and moons in our solar system. The search for evidence of past or present life on Mars, for example, involves looking for chemical signatures similar to those that mark the Great Oxidation Event in Earth's geological record. The deep time perspective provided by the study of the Great Oxidation Event also helps us appreciate the remarkable stability of Earth's environment over the timescales relevant to human civilization. While the event demonstrates that Earth's environment is capable of dramatic changes, it also shows that these changes typically occur over geological timescales that are vast compared to human lifespans. The regulatory mechanisms that were established during the post-oxidation period have maintained atmospheric oxygen concentrations within a relatively narrow range for the past 2 billion years. This stability has provided the consistent environmental conditions necessary for the evolution and persistence of complex life, including eventually the emergence of human intelligence. The scientific understanding of the Great Oxidation Event continues to evolve as new analytical techniques provide increasingly detailed information about this ancient transformation. Advanced mass spectrometry techniques can now measure isotopic ratios in individual mineral grains, providing unprecedented precision in reconstructing ancient environmental conditions. And so we drift back to our present moment, carrying with us the echoes of this vast transformation that unfolded across unimaginable spans of deep time. The Great Oxidation Event stands before us not as a distant curiosity, but as the foundation upon which every breath we take, every heartbeat that sustains us, every complex thought that passes through our minds has been built. In the quiet darkness of space, Earth continues its ancient journey around the sun, its atmosphere now a delicate blue veil that cradles all life in the gentle embrace of oxygen and ozone. That same oxygen that once spelled death for countless billions of organisms now flows through our lungs, powers our cells, and makes possible the intricate dance of consciousness that allows us to contemplate our own origins. The story we have traced through these deep corridors of time reminds us that we are part of something far grander than ourselves, participants in a planetary narrative that began long before the first human footprint marked ancient soil. Every element in our bodies, every molecule that sustains our existence, carries within it the chemical signature of this great transformation, connecting us across billions of years to those pioneering cyanobacteria that first learned to split water and release oxygen into the primordial seas. Perhaps most remarkably, this ancient catastrophe teaches us about the profound resilience and adaptability of life itself. From the ashes of the greatest extinction in Earth's history, arose innovations and possibilities that would have been unimaginable in the anaerobic world that came before. The survivors of this transformation, through countless generations of adaptation and evolution, gave rise to all the beauty and complexity we see around us today. As you rest tonight, breathing easily in air that was once deadly poison, remember that you are the inheritor of an incredible journey through deep time, a living testament to life's capacity for transformation, survival, and renewal across the vast expanses of Earth's ancient history.